Hey everyone, and welcome back to the Deep Dive. Today we're diving into wireless LAN technology, and that means the IE 802.1 standard.
We're going to go beyond just the basics that you already know and really dig into the technical details that sometimes trip people up.
Exactly. And we're joined by our expert to help us unpack some excerpts from Dr. Zelimal Lajiz Hailemariam's work at National Taiwan University. We're going to be focusing specifically on WLAN architecture and that transition from wired to wireless.
Think of it as a bridge between your intro networking class and some of the real-world design challenges that we see with WLANs.
Okay, so let's unpack this a little bit.
Yeah.
We know that in wired LANs, we rely on SysMan-D for collision avoidance.
Mm-hmm.
But when we shift over to wireless, how does that translate?
That's where things get very interesting. Because in a wired environment, we have the luxury of being able to detect collisions directly. But when you move to wireless, you can't have a device listening and transmitting at the same time because of hardware limitations.
I see.
So it's just not possible.
So you can't listen in before you try to jump in. Okay, so what's the solution then?
So we move to this idea of CSMA carrier sense multiple access with collision avoidance. And so it's less about detecting collisions and more about trying to avoid them in the first place.
Okay.
So instead of transmitting immediately upon hearing silence, devices using CSMA will introduce these random back-off periods. So they're essentially pausing to sense the airwaves and make sure there's no one else trying to talk at the same time.
So it's almost like a digital game of not it.
Exactly.
Where they're all kind of like waiting for their turn to jump in.
Yeah, and hoping that no one else chooses the same random back-off time.
Right, because what happens if they do? What if two devices randomly choose the same back-off time?
That's where we introduce this idea of the RTS-CTS handshake. So request to send, clear to send.
Okay.
And you can think about this as a reservation system for the airwaves.
Okay.
So let's say your laptop wants to transmit data. It will first send an RTS message to the access point saying, hey, I'd like to transmit.
So it's kind of like the access point is the traffic cop
Exactly.
of the network?
Exactly. Yeah. And so if the channel is free, then the access point will respond with the CTS message saying, yep, you're clear to go ahead and transmit. And so only then does the device actually start transmitting its data.
Okay, so we've gone from this world of just being able to detect collisions directly to this more, I guess, elegant system of requests and clearances.
It's much more polite.
Yeah. It is a much more polite way of doing things.
Yeah.
But this gets more complex, I imagine, when we start to talk about larger scale WLANs.
Absolutely. When you think about a large office building or university campus, a single access point just won't cut it.
Right.
You need something a lot more scalable. And that's where the idea of these multiple cell WLANs come in.
Multiple cell WLANs. So paint me a picture here. What are we talking about?
So instead of having just one big access point covering everything, you now have a network of smaller interconnected cells, each managed by their own access point. And these cells overlap strategically to provide seamless coverage across the entire area.
Okay, so as you're moving through the building, for instance, your device is seamlessly switching to whichever access point has the strongest signal, kind of like a cellular network, but for Wi-Fi.
That's exactly it. And that's just one piece of the puzzle.
Yeah.
We also need to consider the core components that make up a WLAN. So we've got our access points, obviously. We've got our wireless clients. We have something called the Wireless Distribution System, or WDS. And then, of course, the SASID, which is just a fancy way of saying the network name.
Okay, hold on. WDS, we haven't talked about that yet. What is that?
Right. So the WDS, that's like the unsung hero of large-scale WLANs.
Okay.
What it does is it allows the access points themselves to talk to each other wirelessly. So you don't need to run a cable from every single access point back to the wired network.
Okay, I see. So it helps you extend the reach of that network without having to physically connect everything.
That's it. It's much easier to deploy things that way, especially in large buildings.
Okay, that makes sense. So we've got our access points acting as these traffic cops. We've got our WDS extending the reach of the network. What about the clients themselves? How do they fit into all of this?
So each client, whether it's your laptop, your phone, even an IoT sensor these days, has a wireless network interface card.
Okay.
And that card is responsible for handling the communication with the access point. So it takes care of things like authentication encryption and data transmission.
It's like the client's own little ambassador to the network.
Exactly.
It's handling all the negotiations and making sure everything runs smoothly.
And within that ambassador, we have two key players, the control module, or CM, and the user module, or EUM.
Okay, so break those down for me.
Right. So the CM handles all the behind-the-scenes tasks like scanning for available networks, managing the connection to the access point, making sure everything's secured.
Oh, because it's like the operations manager.
You got it. And then the UM, that's what interacts directly with your operating system and your applications. So it's responsible for passing data back and forth between your web browser, for example, and the wider internet.
So it's like the bridge between what we see on our screens and all the complex stuff happening behind the scenes.
That's a great way to put it.
This is all starting to come together. We've got our infrastructure, our clients, and all these really clever mechanisms that make sure everything runs without a hitch. But we can't forget about one of the most crucial aspects of WLANs, and that's roaming.
Oh, yes, roaming.
How do our devices seamlessly hop between these different cells without us even noticing? It's kind of mind-boggling when you think about it, especially when we're talking about streaming movies or having video calls. We don't want any interruptions.
It seems like magic, but it's actually a very carefully choreographed dance between your device and the network.
Okay, I'm intrigued. Walk me through it.
Okay, so imagine you're walking across campus, streaming a lecture on your phone. As you move, your device is constantly monitoring the signal strength of nearby access points, looking for a better connection.
So it's like your phone is playing hotter or colder with the Wi-Fi signal.
Exactly. And each device has this predefined signal strength threshold that once the signal from its current access point dips below that threshold, is like a trigger goes off.
Okay.
And the device is like, okay, I need to find a new access point, and start searching more actively.
So the lower the signal gets, the more urgently it's searching for a new connection.
Yes, exactly. And once it finds a suitable candidate that's broadcasting the same SSID, then the real magic happens.
Yeah.
The association process.
Okay, this is where it gets really interesting.
Right.
Because we want this handoff to be as seamless as possible.
Absolutely. The last thing we want is for your lecture stream to sputter and die just because you walk down the hallway.
Right, exactly.
So your device has to gracefully disconnect from the current access point and establish a new connection with the stronger one without you ever noticing the difference.
Okay, I'm on the edge of my seat. How does it pull that off?
It all comes down to a really carefully orchestrated sequence of messages. So first, your device will send what's called a disassociation request to the current AP, basically saying, hey, I'm moving on. I found a better signal.
So it's politely bowing out.
Exactly. And at the same time, it's sending an association request to the new access point.
So it's doing this simultaneously.
Yeah, it's all happening in the background. And that new access point will then verify your device's credentials. Just make sure it's not some rogue device trying to sneak onto the network.
Right, got to have those security checks.
Absolutely. And once everything checks out, then the connection is fully established and your data stream continues, hopefully without a hitch.
Wow, that's a lot of back and forth happening in the blink of an eye.
It really is. And it's a testament to the ingenuity of the engineers who design these systems. But as you can imagine, even with these intricate mechanisms, roaming can be tricky.
What kind of challenges are we talking about?
Well, one of the biggest hurdles is latency. Even though those handoffs happen quickly, there's always going to be a slight delay as your device switches between access points.
I see.
For things like web browsing, you probably won't even notice, but for applications where timing is really critical, things like video calls or online gaming, those milliseconds can make a big difference.
Absolutely. I can definitely relate to that. Blaming the internet connection when it's probably a roaming hiccup.
It happens to the best of us. And then there's the issue of authentication. Each time your device connects to a new AP, it often has to go through the whole authentication process again, which can add to the overall delay.
So it's like having to show your ID every time you walk into a different room in the same building.
Exactly. A bit of a hassle, right? Thankfully, there are solutions for that, like pre-authentication.
Pre-authentication. Okay, that sounds interesting. And maybe a little bit like something out of a spy movie.
In a way, it is. Pre-authentication lets your device establish a secure connection with a new access point before it even disconnects from the old one.
So it's like having a VIP pass ready to go.
Exactly. You can breeze through security without missing a beat.
Okay. That's pretty impressive. It seems like WLAN engineers have thought of everything.
We try our best. But there's always room for improvement, especially with the demands on wireless networks constantly increasing.
Absolutely.
And one area that requires a lot of careful consideration is cell design.
Cell design.
Yeah.
Okay, we haven't touched on that too much yet. What's so important about it?
Well, think of it this way. Each one of those cells we've been talking about is like its own little ecosystem. It's radiating that Wi-Fi signal, and the size and the placement of those cells, how much they overlap the materials they have to contend with, all of that plays a huge role in how well the network performs overall.
Okay, so there's a lot more to it than just blanketing an area with Wi-Fi signal.
A lot more. It's about finesse strategy, finding that sweet spot.
I'm sensing a but coming.
You know me too well. The thing is, getting that cell design right is a delicate balancing act. You want to maximize coverage, but not create interference. You need strong signals, but not at the expense of range. It's a real challenge.
This all sounds fascinating and, like you said, very strategic. But unfortunately, it seems like we've reached the end of our bandwidth for part 1 of this deep dive.
I know, we've only just scratched the surface.
Don't worry, though.
Yeah.
We'll be back soon to unravel the intricacies of cell design in part 2.
So as we were saying, cell design, it's really a critical aspect of WLAN performance. It's kind of like the architecture of the invisible.
Oh.
We talk about blanketing an area with Wi-Fi signals, but it's not quite that simple.
Right. It's more about doing it strategically.
Exactly. It's all about finding that sweet spot between coverage, signal strength, minimizing interference. There's a lot to think about.
Okay, so let's break it down a bit. Where do we even begin with something like cell design?
Well, let's start with coverage. That seems like a logical place to start. The coverage area of each cell, we often refer to that as its radius. And that radius isn't just some arbitrary number. We determine that based on a number of factors, and the biggest one is the access point's transmission power.
So a more powerful access point equals a larger coverage area.
In theory, yes. But crank that power up too high and you run into the risk of creating interference with neighboring cells.
Right, because these are radio waves we're dealing with.
Exactly. They can overlap, they can clash, and you end up with a real mess.
So it's like finding the right volume knob setting for your Wi-Fi.
Yeah.
You don't want to blast it so loud that nobody can hear anything.
I like that analogy. And it's not just the access point itself we have to think about. Environmental factors play a huge role as well. Walls, floors, even furniture can attenuate the Wi-Fi signal.
Attenuate.
Weaken, basically.
Got you. So a signal that might travel without any problem across an open office space might really struggle to penetrate a thick concrete wall. That explains why you can have a great connection standing right next to your router, but then struggle to get online if you move to a back corner of your house.
A tale as old as time. And then we also have to factor in which frequency band we're using.
Right, because we have the 2.4 gigahertz and the 5 gigahertz.
Exactly. And those higher frequencies, like the 5 gigahertz, they offer much faster speeds, but they have much shorter ranges compared to the 2.4 gigahertz band. It's a classic trade-off.
So if you're designing a WLAN for, say, a large office building, you might use a mix of 2.4 and 5 gigahertz access points to try to balance those coverage and speed requirements?
That's a very common strategy. Now let's talk a bit about overlapping coverage. We touched on it earlier, but it's worth digging a little deeper.
Okay.
Remember, the goal is to create those seamless handoffs as users move between cells.
Yeah.
We don't want anyone getting stuck in a Wi-Fi dead zone.
Right, exactly. Nobody wants their connection dropping out just because they walk down the hallway.
Exactly. But here's the thing. Too much overlap can be just as problematic as not enough overlap. Well, if you have multiple access points that are all blasting strong signals in the same area, it's like trying to have a conversation at a crowded party.
Too many people talking at once and nobody can understand each other.
Exactly. You end up with a lot of interference, which degrades the overall performance of the network.
Okay, so it's all about finding that balance.
Finding that sweet spot. And then on top of all of that, we also need to think about capacity planning. Remember those lecture halls packed with students all trying to use the Wi-Fi at the same time?
Oh, yeah. Recipe for disaster.
Right. A single access point, even if it has a really strong signal, can only handle so many simultaneous connections. It's like trying to squeeze a whole stadium's worth of people through a single turnstile.
So how do you avoid that bottleneck?
That's where careful cell design comes in. By strategically placing those access points and adjusting their configurations, engineers can distribute the network load more evenly, make sure that everyone gets a decent slice of that Wi-Fi pie.
So you're not just putting up access points wherever you can find space. You're really thinking strategically about where they're going to have the most impact.
Absolutely. It's all about strategy. And, we've been really laser-focused on the technical aspects here, but it's important to remember that these networks are more than just a collection of cables and signals.
That's a good point. We often take it for granted, but Wi-Fi has become as essential as electricity in a lot of ways.
It really has. Think about all the different ways that WLANs are being used today. In hospitals, they're enabling doctors and nurses to access patient records in real time, which obviously has a huge impact on patient care.
And then there's education. Everything from online research to remote learning relies on having a robust WLAN.
Exactly. And let's not forget about the retail sector. Imagine a busy shopping mall with all those stores, all those shoppers. WLANs are powering everything from those mobile point-of-sale systems to inventory management, even those targeted ads that seem to follow you around.
Okay, maybe let's not dwell on the targeted ads.
Fair enough. But the point is WLANs are everywhere. They've become absolutely essential infrastructure.
They really have. And as we move towards this future where we have billions of devices connected to the internet, I mean, everything from smart refrigerators to self-driving cars, the demands on these networks are only going to increase.
Absolutely. It's both incredibly exciting and a little bit daunting.
It really is. It makes you wonder how we're going to design WLANs that are robust and adaptable enough to handle the demands of this interconnected future.
It's a question we're all grappling with, and one that we'll be exploring further in part 3 of this deep dive.
Okay, so stay tuned because we're going even deeper into the future of WLAN design when we come back. Welcome back to the deep dive. We've been on quite a journey through the world of WLANs, from those collision avoidance mechanisms to the complexities of cell design, and now it's time to look ahead. What does the future hold for this technology?
Well, the future of WLANs is inextricably linked with this idea of the Internet of Things, the IoT.
Right, everything's getting connected.
Exactly. We're talking about a world where we have billions of devices all communicating with each other, and not just computers and phones, but everyday objects.
Right, refrigerators, thermostats, our cars even.
Exactly. Everything's going to be generating data, transmitting data, and that has huge implications for how we design these WLANs.
So it's not just about scaling up what we already have, it's about rethinking the whole approach.
Absolutely. Current WLANs, they're primarily designed for what we call human-centric traffic, things like browsing the web, streaming videos, having those video calls. But IoT devices, they have a different set of needs.
So what are we talking about here? How are they different?
Well, for starters, a lot of these IoT devices, they transmit data in small bursts, very intermittently.
Okay.
It's not like your laptop that's constantly streaming data. It might be a sensor on a factory floor that's just sending a temperature reading every few minutes.
So not exactly Netflix.
No, not quite. And these devices might be battery powered, so energy efficiency is absolutely paramount. We can't have our smart thermostats and then there's the issue of security.
Right. Even more devices means even more potential vulnerabilities.
Exactly. When you think about it, a compromised sensor in a power plant, for instance, that could have catastrophic consequences.
Okay, yeah, the stakes are definitely higher.
Absolutely. It's not just about protecting personal information anymore. It's about critical infrastructure. So we need incredibly robust authentication encryption mechanisms to prevent those data breaches.
So security is more important than ever.
It's paramount. And then on top of that, we also have to think about latency.
Right, because some of these IoT applications are very time sensitive.
Extremely. Think about things like remote surgery or autonomous vehicles. We're talking about split-second decisions being made based on the data these networks are transmitting.
So even a slight delay could be disastrous.
Absolutely. So we need those latencies to be as low as physically possible.
That's a lot to juggle.
Yeah.
So how are engineers actually tackling these challenges? Where do you even begin?
Well, one very promising avenue is the development of these new WLAN standards, specifically designed for IoT devices. You've probably heard of Wi-Fi 6.
Sure.
But get ready for Wi-Fi 7 and beyond.
Okay, so new and improved Wi-Fi standards. What can we expect from those?
We're talking about faster speeds, lower latency, improved power efficiency. These new standards are really pushing the boundaries. They're utilizing technologies like OFDMA, for example, orthogonal frequency division, multiple access.
OFDMA?
It's a mouthful, I know. But essentially, it's a much more sophisticated way of dividing up the available bandwidth, allowing multiple devices to transmit and receive simultaneously without interfering with each other.
So it's like upgrading from a two-lane road to a multi-lane highway for our Wi-Fi signals.
That's a great way to put it. And to address the security concerns we were talking about, these new standards are incorporating really robust encryption and authentication protocols.
Okay, so that's one piece of the puzzle. What else is on the horizon?
Well, another really exciting development is this idea of mesh networks.
Mesh networks. Have you heard of those?
I've heard the term, but I'm not entirely sure how they work.
Okay, so imagine a network where every single IoT device can act as a node, relaying data to its neighbors.
So it's not just relying on a single access point to handle all the traffic.
Exactly.
Yeah.
It creates this self-healing, decentralized network. It's much more resilient.
So even if one device goes down, the others can pick up the slack.
Exactly. And it also means that you can have much better coverage because the signal is being propagated through multiple devices.
So it's like the Wi-Fi version of teamwork.
Exactly. And then as we generate more and more data, this idea of edge computing is becoming increasingly important.
Edge computing, so that's processing data closer to where it's generated, right?
Exactly.
Yeah.
Instead of sending all that data to the cloud for processing, what if we could do it locally on the devices themselves or on servers that are much closer to the edge of the network? Right, so it reduces the strain on the network as a whole.
Exactly. And it also reduces latency because that data doesn't have to travel as far.
Okay, so that makes a lot of sense.
Yeah.
Especially for those time-sensitive applications we were talking about.
If you think about those self-driving cars, they can't afford to be sending data back and forth to a data center hundreds of miles away. They need those decisions to be made in real time.
That's incredible. It really seems like the possibilities are endless. So as we wrap up this deep dive, what's the key takeaway here? What should we be most excited about when it comes to the future of WLANs?
I think the most exciting thing is just how much innovation is happening in this space. The demand for faster, more reliable, more secure wireless connectivity is only going to increase.
Absolutely. A huge thank you to our expert for guiding us through this incredible world of WLANs.
My pleasure.
It's amazing to think about all the complexity that goes on behind the scenes to keep us connected.
It's a hidden world.
And to our listeners, thank you for joining us on this deep dive into the world of wireless LAN technology. We'll be back soon with another fascinating topic. Until then, keep those curiosity circuits firing.